Hey everybody, this is the second of the three videos I'll be making for the final exam extra help review. In this one I'm looking over Learning Target 14, which is all about optimization. So similar to the last set where I looked at Learning Target 8, I'm going to start out with a checkpoint problem, this one specifically from checkpoint 5. And as I said before, I do recommend you try these problems out before watching this video. I'll have those documents somewhere on the Canvas page, whether it's announcements or files, and also I'll try to get them in the video description here on YouTube. Okay, let's jump in. So we have an airline policy that says all bags must be box-shaped with the sum of length, width, and height not exceeding 64 inches. And we need to figure out the dimensions of a square-based box with the greatest volume. So optimization problem. We're given that the volume of a box is length times width times height, but in a picture below we can see, since it's a square-based box, it's effectively width times height. So our constraint, we know that the length plus the width plus the height cannot exceed 64 inches, but we know we're trying to maximize, so it will be equal to, we'll say. But since the base of this box is a square, we can write this as W plus W plus H is equal to 64. And our objective is to maximize the volume. So our objective function is the width times the height. Okay, so pretty much all optimization problems, we're going to have this constraint and then objective. And our objective currently is in terms of two variables, W and H. So we'll need to use our constraint function, solve for one of those variables, and put it into the objective. It's not too bad. First, I'm just going to simplify the constraint function a little bit, and we'll have 2W plus H equals 64. I'm going to solve for H. I think it'll be a little bit easier. It's pretty arbitrary which one you want to do, but I'm going to solve for H, so 64 minus 2W. And then plugging into our objective function, we'll have V is equal to W squared, that's W times W. And then our H is 64 minus 2W. Expanding that out, we'll have 64W squared minus 2W cubed. Okay, and then for all these optimization problems, we'll take the derivative. So V prime is going to be equal to 128W minus 6W squared. That just comes from the power rule. And since we're maximizing, we're basically looking for critical points. So we're going to set equal to 0. Looking at this, I know I can factor out a W, and how about a 2 as well? So I'll have 2W. That leaves 64 minus 3W equal to 0. So since I have basically two factors set equal to 0, I can write them independently, but I'll have 2W equals 0, so W equals 0. But this is trivial, just based on this image right here. If W is equal to 0, then we don't have a box at all, and that doesn't make any sense. So cancel that out, or forget about it. So the other factor is probably going to be the one we're going to use, 64 minus 3W equals 0. So W equals 64 over 3. Okay, well this is the only value that the equation spits out, but it's always good to double check and use a sign chart just to make sure we actually have a maximum, because we're trying to maximize volume. So you have V prime, little number line there, and our point is 64 over 3. Since this is the only critical point that we found, we can really try any numbers when we plug in. I'm just going to use 1 and 50, because I know 1 is less than 64 over 3, and I know 50 is greater than it. And all we're really looking at is the sign now. But so we're going to be looking at V prime, and 2 times 1, and then 64 minus 3 times 1. I don't need to actually solve for the value. I just know 2 times 1 in terms of like factors, that's a positive. 64 minus 3 times 1, that's a positive. And then a positive times a positive yields a positive. So this is positive here. Then if I have 50, I'll have 2 times 50, which is a positive. And then 64 minus 3 times 50. Since 3 times 50 is greater than 64, this factor is negative, and positive times a negative is a negative. So going from positive to negative at 64 over 3 means this is indeed a maximum. We give this a big check mark. So we know that W is equal to 64 over 3 inches. But we need all the dimensions. It tells us, well, I guess dimensions plural. So we can solve for H. And I have this handy function, or handy equation here, H equals 64 minus 2W. So 64 minus 2 times 64 over 3. This is probably all right in terms of submitting. I think that was accepted on the checkpoint 5 when he did it. But just for your reference, it is also equivalent to 64 over 3. Apologize for a little bit of the handwriting. Got a bit sloppy throughout there, but I think it's legible enough. But that's the first problem from checkpoint 5. Pretty much all optimization problems, you just get a constraint function, an objective function, and you solve that constraint function for one of the values and plug it into the objective so that your objective is a function of only one variable. From there, you'll take its derivative, set it equal to 0, find those critical points, check those critical points with the sign chart, and make sure you get all the values that it asks for. And yeah, that's it. Okay, now we'll move on to the second problem, Monaco Grand Prix. So, due to the narrow streets of Monte Carlo, success in Formula One's Monaco Grand Prix often comes down to qualifying, as passing on race pace alone is quite difficult. So before the qualifying session, Ferrari adjusts both the engine power setting and the aerodynamic downforce level, all to balance speed, cornering grip, and fuel usage for the drivers. So we're going to let X denote the engine power setting in arbitrary units, and then Y will be the downforce level, which is also dimensionless. So based on prior testing data, Ferrari models an overall performance efficiency score by this function here. P of x and y equals 30x plus 5y minus x squared. And because of limits on fuel consumption and drag, the setup must satisfy the constraint of 2x plus y equals 60. And both x and y will be positive numbers. So we're asked what engine power x and downforce level y will maximize the performance efficiency score and help Charles Leclerc or Lewis Hamilton win the race. Okay, so a lot of information there, but same steps as before. We need a constraint, we need an objective. So a constraint, I guess it says it pretty clearly, will be 2x plus y equals 60. And our objective is to maximize performance, so we'll use that equation there. P equals 30x plus 5y minus x squared. From here, honestly, a lot of these optimization questions are pretty repetitive. So we're just going to solve our constraint for a term, or for in terms of one variable, and then plug in our objective. So I think solving for y will be a little easier, but it really doesn't matter too much. We'll have 60 minus 2x, and then plug that into p. So I'll have p equals 30x plus 5 times quantity is 60 minus 2x minus x squared. Simplifying that a little bit more, we'll have 30x plus 300 minus 10x minus x squared. So all of that is equal to negative x squared plus 20x plus 300. Okay, now we differentiate. So p prime will just be negative 2x plus 20. We'll set that equal to 0, find our critical points, and we'll have x equals 10. So only one value to test here, but we'll still set up our sign chart for p prime. And I'll test 0, so it's less than 10, and I don't know, 20. So plugging into p prime equals negative 2. We'll test 0, and we just get 20, which is positive. And then p prime for 20 is negative 2 times 20 plus 20. And that's going to be equal to negative 20, which is a negative number. Does this make sense? We have positive, then negative p prime, so it's increasing, then it's decreasing, which means we have a max, which is good. So we know x equals 10, but we also need to find y per the problem statement, but y is just equal to 60 minus 2x. So y is equal to 40. Pretty simple there. That was not too bad at all. Honestly, pretty similar to number 1. In this case, the equations are all spelled out pretty easily to understand, so it's not too bad at all. But I guess we'll just jump into number 3 then. Arsenal 3, Real Madrid 0. Interesting. So we had at the first leg of the Champions League quarterfinal, Declan Rice scored not one, but 2 great free kicks past Real Madrid's goalkeeper, Thibaut Courtois. The second was actually nominated for the Puskas Award, which is an award for the best goal in the world for a given year. Looking at the strike from the side, where Declan Rice, the free kick taker, is the origin of an XY plane, this shot is initially on a trajectory described by the function 1/4 of x. This is obviously a pretty big simplification. One, because the ball wouldn't be exactly linear with spin and gravity, and even more so if we assume that it's 1/4 x, I mean it's always going to rise forever, which it doesn't. It would dip back down, but for this problem, we're only looking at the initial strike, so we'll simplify it as 1/4 x. Then we're told at the top of the wall, which a wall is comprised of defenders to block the shot, it's set at 10-2. And that's in terms of yards, if that wasn't previously said. I guess it really doesn't matter, but for soccer fans, like the wall, it has to be 10 yards away from the shot. So 10-2, about 2 meters tall. And we need to find the closest point Declan's strike is to the top of the wall. Okay. So our constraint function here, we know that the shot will be on the trajectory described by 1 equals 1/4 x. But now the objective is a little bit harder to understand because it doesn't spell it out for us clearly, but we know we're looking for the closest point of Declan's strike to the top of the wall. So I'm thinking distance function here, distance equation. And that's defined as d equals the square root of x minus 10, because that's the point of the wall. That's squared, plus y minus 2, also squared. And since we're just trying to minimize this distance, we're able to square both sides. So I'll just say, we'll call it uppercase D, and we'll just have x minus 10 squared plus y minus 2 squared. I remember when I took calculus, this always tripped me up a little bit, like why can we just square both sides and solve it out that way? But if we're minimizing D and we square D, we have D squared. But a minimized value of D would be the exact same as minimizing D squared. It's not too much of an issue there, just I highly recommend doing so, or else this would be quite a pain to solve. But anyways, we have our objective function now, we have our constraint function now, and we can plug into, plug a constraint into the distance equation to get it in terms of one variable. So that means we will have d equals x minus 10 squared plus replacing y with 1/4 x minus 2 squared. Okay, bit of some annoying arithmetic here. We just got to factor this out. We'll have x squared minus 20x plus 100 for that first term, plus 1/16 x squared minus x plus 4. And then combining like terms, we'll end up getting 17/16 x squared minus 21x plus 104. Okay, that is our distance function in terms of one variable x. And now we'll derive it or differentiate on both sides. So this leaves us bringing that 2 out in front with the power rule of 17/8 x minus 21 equals 0. So 17 over 8x equals 21. So multiplying it 8 over, we get x equals 168 over 17. I'm kind of skipping some of this arithmetic, which I typically work out a little bit more, but it's not super important to the context of the problem, or in terms of the context of actually doing the optimization. So I'm just going to not waste anybody's time with that. But anyways, we have our x value, just one x value, and we'll do another sign chart. These may seem a little bit repetitive, but there could be questions where you don't have only one critical point, you could have multiple. In those cases, you'd absolutely have to do this just to check. Okay, we'll test 0 and 100. Since I know 0 is less than 168 over 17, and I know 100 is more, I'm just going to assume that we're not using a calculator for this. So I don't really know exactly what 168 over 17 evaluates to, but I know that 0 will be less and 100 will be more. And if I were to plug that 0 into our distance equation here, this first term would go away and we'd have negative 21, which means we'd have a negative. And then if I plugged 100 in, this value would be greater than this would be greater than 21. So assume it's a positive. Not just assume, but we know it's positive. And this is telling us that 168 over 17 is a minimum, whereas in problems 1 and 2, those are maximums. But this is good because we're trying to find the closest point of the strike. We're trying to minimize that distance. So that means we know x is 168 over 17. That's the first point. And then back to our initial constraint function, y equals 1/4 x. Y equals 1/4 of 168 over 17. Once again, skipping a little bit of arithmetic, we have 42 over 17. I guess the question actually asks for the closest point. So we can also write this in point form. So x comma y, 168 over 17, comma 42 over 17. And that's that problem. And that's the whole problem set, actually. So overall, big takeaways for this learning target. I think there's a lot of similarities in all these problems. Figuring out and recognizing constraint and objective, solving that constraint for one variable, then plugging into the objectives in terms of one variable, differentiating that, finding your critical points, testing your critical points to make sure it's maximum or minimum or whatever you're looking to achieve, and then finding whatever other variables are being asked for. In this case, I think all three questions, ask for like two different numbers, a width or a height or a power level or a point. So overall, I would say with these optimization problems, just don't get too freaked out. I think it's definitely a good application of the calculus we've learned, but overall, the actual arithmetic and the solving isn't too bad.